Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's get started. So it's my pleasure to introduce Matthias Perrin from University of Werimag, France. So Matthias is a student working with Dr. Nicolas Olwash, and he's interested in abstract interpretation and static analysis of numerical programs. And today he's going to tell us about some exciting work that he has done recently on proving properties of arrays.
Exactly. Thank you for your introduction. So, yes, feel free to interrupt me if you have some questions. Yeah, sure.
How do you pronounce Hagwash?
Yeah, it was the same question before. Alvax. Yeah. A well-known family in France. So, explanation of the title is, in this work, by discovering, we mean in a fully automatic way, properties about the contents of arrays. So, for example, sort properties, about the values that are in the array. And of course, we had to focus on a restricted class of programs, which we have named simple programs. So here is a piece of code that belongs to this class of programs. Don't try to understand it at the moment. Just see that there is only one-dimensional arrays that are indexed by a constant or the sum of a variable and a constant. The variable, I will say, index. And then that indices progression or incrementation or decrementation. So here are the flavor of our simple programs. So if now I tell you that this piece of code is find algorithm, the segmentation phase of quicksort, you will expect static analyzer to give you at the end of the program the following invariant. So it's not all the invariant, but at least a property about indices that I is between the bounds of the array A, and a property about the values in the array. The property is the values of array A are segmented with respect to pivot value X. So here you can define it using one universally quantified variable L, saying that at left of cell I, all values are low equal to X. At right, they are strictly greater than X. Let's see another example of simple program, which is insertion sort algorithm, which fall into the class of simple programs. So here, the property you want to discover at the end of the program is that the array is sorted. And here, the property to discover about arrays is relational. And you can say it saying that for the value at one cell is greater than the value at the precedent cell. Yes?
So this is a loop invariant for the outer?
No, it is the invariant that you expect at the end of the program. So, yeah, the invariant inside is much more intricate. Sure. So here are the simple programs we want to analyze and the flavor of the properties we want to discover. So we choose the abstract interpretation framework to reach this objective, to discover these properties. First, I have to say that about the properties about indices are not too hard to discover for this class of program. It has been widely studied. It's not the case for contents about the arrays. So I will go through some existing abstract domains that handle this kind of properties and explaining our proposition. So here on this slide, I put on the right part of this slide the view the abstract domains have of arrays. And at the left side, the variables on which the abstract value is built. So first, in an increasing order of expressiveness, you have summarization techniques, which consist to abstract each array A by a scalar variable that you manage with other scalar variables but with a different interpretation and different transfer functions. So here, for example, you have that A is between 1 and 5, which means that all the values of the array A are between 1 and 5. And of course, an assignment to one cell will be a weak assignment to the variable A, which can be viewed as an undeterministic assignment to the variable A. So for example, if you know that all the values in your array are greater than 10, and you assign value 9 at one cell of the array, you can only say that all the values are greater than 9. So here, in this abstraction, you can only lose information due to this weak assignment, and you cannot gain information from conditionals about array cells. Moreover, you can only express unary properties, so just about one cell in your array properties. So an improvement was proposed in 2005. Yes?
So on the previous techniques, how do you even gain any information if you can only lose information?
You can, okay. Due to the weak assignment, you join the
That I understand. So what I'm asking
Yeah.
is that I'm surprised that this technique works even for any example, because how do you even gain any information?
Okay, so of course, these techniques assume that at the beginning of the analysis, you're able to say what is in your array. So it needs a tricky analysis before. So it's very, yeah, sure. So,
Just a second,
yeah.
can you go back to one more slide more? So what is the domain of the new variable?
Oh, what you want.
So it's user chosen.
It's, for example, you take a certain lattice and you manage your variable that abstracts your array with other variables. So, for example, if you know that all your values are, you have only ones in your array, you will have A equal 1, and it could be that you will have A equal n or something like that because n is equal 1. So,
Okay, so you can choose either inequalities or
you can choose inequalities, octagons, what you want. Just the interpretation and the transfer function of these scalar variables are different. So, indeed, it's not a clear separation with other properties, a thing we will avoid. So the improvement proposed in 2005 by Gopan, Reps, and Sagiv is to consider a symbolic partition of your array and to attach to each symbolic slice a scalar variable just as before. So here the interpretation of scalar variable A1, which is here between 1 and 5, means for all cells strictly lower than I, the values in this subpart of the array are between 1 and 5. And then, of course, the idea behind symbolic partitioning is to avoid all weak assignments. So if you have an assignment in your program to cell I, you expect to have in your symbolic partition a symbolic single slice representing cell I. So here, in this example, this symbolic slice is A2, and if we make this assignment to cell I, we will only assign A2 and leaving unchanged A1 and A3. So here you gain the information. Yeah, oh, figures.
How do you partition this space?
So there is a first step. You syntactically read your program, and at every assignment, the access you have here at the left of the assignment, you cut your partition with respect to this expression. So if here it is I plus 3, you will cut with strictly lower than I plus 3 equal I plus 3 and strictly greater than A plus 3.
But initially, how do we infer that partitions? How can you say
Just syntactically looking at your program.
Okay, so it has to be given. It's not automatic.
Yes, it is. It's a first step of your analysis. You decide the partition,
I see.
and then you conduct the Fixpoint computation.
I understand.
Yeah, we will see that after. Yeah.
There are only 3 partitions always?
No. You can have a partition with another indices. We will see that after. Yeah.
But then strong assignment is assuming that this partition only has one element.
Yeah, exactly. It's a single one. Sure.
So if we have 2 variables, 2 index variables, I and j,
Yeah.
then we have to distinguish the case whether I equals j
Sure.
or not.
It will lead you to have 9 symbolic slices if you cut with respect to I and j, for example. We will see that. Yeah.
I don't quite see where you lose precision here.
Where I lose precision.
Yes.
Okay. If, for example, it's about when I will move, when you will do an incrementation or a decrementation of I, you have to change the property that hold on this symbolic slice, for example, if you increment I. Okay?
Yes.
So basically, we will see that you have to join the property that holds here and here.
Okay.
So here you lose the information.
And a single block of partition, should it be contiguous or can it be any set?
Now, it only can be a contiguous.
So if you have 2 index variables I and j, then you can't possibly do this strong assignment unless you know that I not equal to j.
Yeah, sure. Okay.
So the strong assignment, yes, so strong assignment is making more than one assumption. So one assumption is that
Sure.
the partition should contain only one element, but if you have other partitions that contain one element, then it should be disjoint.
Exactly. Yeah. You will basically distinguish the case when I is strictly lower than j and things like that. So here you can only express unary properties, just as before. Well, I must say that you have a kind of relational properties, but holds with not an element-wise semantics. For example, if here I had A2 equals 6, I will have A2 is greater than A1, but it means that all the values of first symbolic size are lower than equal than the values of
Between partitions.
between symbolic slices, but not with an element-wise semantics, which appear very important to discover the properties we want. Then you can check, not discover. You can check user-defined relational properties, such as array A and B are element-wise equal, thanks to the symbolic partitioning. So you have your abstract values, just as defined here, and some set of formulas that the user give, and it is checked during the analysis that the formula is always true. Yes?
So I don't understand. So how is this relational formula representable using these partitions?
No, it's not. It's not representable in the abstract values using these scalar variables. But you can have a formula which takes its value into a free-valued logic. So at the beginning of the analysis, for example, to analyze that array A and B are equal in a array copy. So at the beginning, you will have I equal 1, and you will say that I don't know for this formula. And then you will consider I equal 2, and you will see that you have just one cell, and here it holds because you have just did the assignment.
But are we considering the partitions over array A or over array B in this case?
Sorry?
So are we looking at the partition of
Yeah.
array A, or are we looking at the partition of array B? When you are checking that.
Okay, it is here the same partition for all arrays. So you will have basically another scalar variable B1, B2, B3, and you will have, but you will not consider that B1 equals A1. It's really, you have these abstract values, and then on top of this, they try to check some relational properties. So they construct the idea to have some properties that can be checked during the fixed point computation, but it's not more. Basically, thanks to the symbolic partition, you can make induction, and so you can check this kind of properties. And then there is the work you did in 2008 with McCloskey and Tiwari. And here, the idea of an abstract value is a set of formulas using one or more universally quantified variables, here key 1 and key 2. And these abstract values are highly expressive. So for example, to say that this subpart of the array is sorted, you can say that for all k1, k2, such that k1 is strictly lower than k2, the value at k1 is lower lower than the value at k2. So, due to this highly expressiveness of the abstract values, and moreover, the space of value for k1 and k for your quantified variables can be very intricate. The properties about arrays can only be inferred. You have to guide the analysis and give some templates which aim to say where the quantification will appear and what is the form of the properties you want to discover. So here was the problem they have. And then no such expressiveness is always required. So for example, to say that this subpart of the array is sorted, you can say just as before with one universally quantified variable. And it is just like this they do to analyze, for example, insertion sort algorithm, if I remember well, yeah.
So one that I would like to add as a comment
sure.
Is that even though this invariant looks to represent essentially the same property with just one quantified variable, proving that, let's say, a of 0 is less than equal to a of n is not trivial from this quantified invariant.
Sure.
But it is actually easier from the one that
I will have said it, sure. Okay. Of course. Here you will limit the induction to, and you cannot accept all what you want of your property, and that's a really tricky, really intricate problem. But you can leave this part to another tool. Here is the idea we have. So what is our idea is that the properties about arrays is less uniform than the properties you have to find on the indices. So we focused on fixed the properties about indices using symbolic partitioning, and try to find automatically the properties about arrays. So how? Yeah.
So I don't here quite understand what is a template. Should it appear also on the right side of the?
On the right side of implications, sure.
And what is allowed as a template?
Oh, okay. So basically, there are parameters of the analysis. So you have some lattices to represent properties of the left side of the implication on the right side of the implication. And then I think the template you can express depends of this lattice.
So I think that answers the question that you asked. A template is essentially a formula with some poles, and then you introduce fresh variables in those poles, and then you can quantify over those fresh variables. So template is a context, a formula with poles.
Sure.
So that you have arrays there is just an application.
Just an application. Arrays is just an application.
It's not so the scalability results are not dependent on the form of the template.
So we assume that you have a decision procedure for the underlying theory, and you have some other operations for the underlying theory, and we use them as black boxes.
Okay.
But you can also have reachability. You can also iterate over
Sure.
this.
Yes, you can also reachability. So yes,
that's not a template, but that's more of abstract formula that you can write down that your abstract domain can manipulate. So quantified invariant consists of, in this case, two parts: the right side of implication, the left side of implication. The right side of implication is a template, a formula with codes that you quantify over, and the left side is any arbitrary abstract element for which you have an abstract interpreter.
Okay.
At least you hope it will handle the difference of variables bounded by a constant to express that, to express a symbolic partitioning. That's the idea. So here, yes, we want to take advantage of the symbolic partition technique, and we will not attach to each symbolic slice a scalar variable, but a formula representing the properties about arrays that hold on this symbolic slice. So for example, here we have mu1, this formula about the first symbolic slice, which says that b is between a and a plus 5. Which means, because we give element-wise, clear element-wise semantics to these formulas, that for all cells at left of cell I, the value at one cell in B is between the value at the same cell in A and this value plus 5. And just as before, you expect that all your assignment will be strong assignment, so you have to decide kindly your partition for that. And a strong assignment is a change in the right formula, here mu2, making the assignment the expected assignment in this formula. So here you can express relational properties, just as you have seen. And this property, that's why I put our abstract domain here, or much more or less expresses that the properties in quantified abstract domain, in universally quantified abstract domain, because they strictly hold within the same symbolic slice. So the question will be how we will express sort properties in this scheme. So we will have to basically express that this slice is strictly lower than this slice with an element-wise semantic. We will see that furthermore. So in a more formal way, what are our abstract values? So I remember you the properties we want to discover are a conjunction of a property about indices, row, and a set of properties about arrays, where arrays appear just like this, A, L plus a constant. So our abstract value have parameters. So we consider a lattice to express the property about indices, Ln, and a lattice to express the properties about content, Lc. Then an abstract value can be understood only with respect to a symbolic partition, which will be represented by a set of formula phi p, which are elements of Ln. So for example, that L is between 1 and I. And then to each symbolic slice, we attach a slice property, mu p, an element of lattice Lc, where access to array A at cell L plus C is represented by a scalar variable A to the C. So for example, A at L plus 1 will be represented by A to the 1. So just to summarize, an abstract value is understood with respect to a partition, and it's a conjunction of a property about indices and a set of properties about arrays. So here are some examples. For as parameters for the lattice of indices, we take potential constraints, so the difference of two variables is bounded by a constant. And for the lattice of contents, we take equation. So here there is a partition, a simple one, we just cut with respect to I. And then we can focus on the abstract value, where we have the property about indices, I is between 1 and n. mu2 and mu3 are at top, which means that on this subpart of the array, I don't know what it is in. And we have mu1 saying that A and B are element-wise equal on this subpart of the array. So take care that if I change the property about indices, for example, that I equal n plus 1, symbolic slice phi2 and phi3 are unfeasible, and they do not represent possible cells. So in this case, we normalize their slice property to bottom value, and we will see why it's a good choice after. And the interpretation of such abstract value is that A and B are element-wise equal. Another example with a sort property. So if we have to express a sort property, we need at least comparisons for LC, and a little bit more intricate partition where I can only go from cell 2 to n. So there is one more symbolic slice. So here we have that I is between 2 and n, and we have the sort property in mu2 saying that, okay, which is A minus 1 is low equal to A0, which means that this subpart of the array is sorted. So see that here, when you do, for example, if you have a strong assignment to do at cell 1, it will change what you know about A minus 1, because A minus 1 represents this symbolic slice. So the strong assignment in this cell will be a weak assignment on scalar variable A minus 1. So we do not avoid all weak assignment in this scheme of abstraction. So how the analysis works? So first we have to decide the partition, and then we have to make the fixed point computation. So here is an example how we decide the partition of maximum search algorithm. So first, at each control point, we attach a symbolic partition. So at the first control point, we have one symbolic slice representing the whole array. And then we have some heuristics. So we take care about indices initialization. So here is initialized to 2, and its progression. So here we see that the subpart of the array from cell 2 to n is of interest. So we cut with respect to this subpart. And then, to avoid weak assignment and to gain information from all conditionals, so here, for example, we have a guard about AI, we will cut with respect to I. And here we know that I is between 2 to n, so we will not consider other cases here for first cell. So yes, it's that. If you have at one control point partitioning with respect to I, and then you have to cut with respect to j, for example, because you have an assignment to this cell, you have to distinguish all possible cases. So it will leads to under 9 symbolic slices. So you can avoid to distinguish all cases. For example, if you conduct first an analysis only on the indices, and then, for example, you will know that j is ever low or equal to I. So you can avoid to avoid some symbolic slices. It's the case in insertion sort algorithm. So how insertion sort works? In the outer loop, you have this symbolic partitioning where you know that I is always between 2 and n. And, okay, you know that the array is sorted till cell I, and you will consider the value at I, and you will put it at the right place using index j. So in the inner loop, you will have j and j plus 1 to make the key value at the right place. And then you will have to consider these symbolic slices, because sometimes j, you know that j is always strictly lower or equal than I, strictly lower than I, sorry. So you have this, for example, symbolic slice to handle that, say, I equal j plus 1 sometimes. So, yeah, if you eliminate L in your formulas 5p, it will give you all the disjunctive cases we take into account. So now, after deciding the partition, how Fixpoint computation work, so here we have a simple program which copy array B into array A. So at the right side, I put the abstract value at each control point. Sorry, first column is the property about indices, and other colors are the columns or properties about arrays. And below, I put the symbolic partition we have. So we have an assignment to cell I. So we have a cut of the symbolic partition with respect to I. So first, we have that I equal 1 here, and mu2 and mu3 are at top, because we suppose that we suppose nothing about the contents of the array. Mu1 is at bottom by normalization. Then we obtain that I is low equal to n, and then come the assignment. So the assignment will give us in mu2 the equality of A and B. Then we have the incrementation. So how does incrementation work? In the general case, here you have I incremented by 1, and you see that the property that holds on this subpart of the array is the join of mu1 and mu2, and the property that holds on these two symbolic slices are mu3. So here, in our example, it gives us the join of this equality and bottom value. So that's why bottom value was a good choice for empty symbolic slices. So we keep here, we have our invariant for I equal 2. And then we want to have the convergence of the loop, so we have to join this property and this property. Okay, so how does join work on on array properties? It's only the join symbolic slice by symbolic slice of the properties into the array. So we have I is between 1 and 2, and the equality on mu1. Then we have to apply a widening to have termination of the fixed point computation. So we have I is between 1 and n, and here the widening gives us always the equality. And then we continue. We have the assignment. So we have equality in mu1 and mu2. And then incrementation will join these two properties from mu1. So we keep the equality property. Then we obtain the convergence. And at the end of the loop, we have that I equal n plus 1. And the interpretation is that A and B are element-wise equal. So I put a slide here more about, more technical, just to know, okay, the question was how much we have to deduce from our abstract values, because you, as you said before, you cannot, you have to choose a deduction procedure that do not go too far, because although you will have to consider too much cases. So here it is at the bottom of the slide. If I have, for example, a partition with I and I plus 3, and I know here that a to the 3 equals 5, normalization will give me that A0 here is 5. But if I have A2 equals 5, I will not have that I minus 1 equal 5 here. So here is how we manage the complexity. Then there is also some properties that does not depend on our special variable L. So it is a case of the scalar properties you can find in your abstract value. So for example, you know that here A0 equal X because AI equal X at some point of your program. So if you consider to eliminate L in phi 1, sorry, so this property, for example, okay, sorry, I eliminate here in this symbolic partition all L. So what does it give? It gives me that I is greater than 2 if I want this symbolic slice to exist, and here that I is greater than 1 for these two symbolic slices. So if I have I is greater than I implies, I don't know, x equals 5, then if I is greater than 2, it implies that I is greater than 1, and it has to imply that x is greater than 5 also, x equals 5 also. So the scalar properties you have here must be scalar properties here. So finally, it's time about results. So here is the list of simple programs we fully analyze using potential constraints as lattice Ln and Lc. So first we have simple one-loop programs analyzed like array copy, maximal search algorithm in quite good time. Then we had a surprise with this example, which is a sentinel. So you're looking for a value in your array, and you put this value at the end to avoid to exceed the bounds of your array during your search. So basically, you want to be sure here to putting the value you're looking for x at the end of your array, that I is always between 1 and n. So it's interesting because it is a property about arrays that involves a property about indices. So, yeah. So here it is analyzed also in a good time. And then we have more intricate simple programs, more intricate programs, which are insertion sort or find the segmentation phase of quicksort. Our claim is that these little programs are a good representative of what you do with arrays in much more bigger program. You will not have more than 4 or 3 nested loops in your programs. But yeah, analysis time are only reasonable, and they are sensitive to the number of slices you have to consider in your symbolic partition. So here you have 10, and here you have 14, and times is 3 more. You have a 3 factor between the 2 times. Indeed, the complexity of the analysis is n to the 4 is n to the 4, where n is the number of symbolic slices you have. So it's important.
And how does the number of symbolic slices depend, for example, of number of nested loops?
Yeah, of course. If you have 2 loops, probably you will have to have considered 2 indices in your. So we'll have at least 9 symbolic slices, things like that. So I will conclude and then doing the demo. So achievements, we fully automatic discovery properties about the contents of arrays on a restricted class of programs. We hope to extend this class considering loops with steps. So for example, incrementation of indices by 2. But for that, we have to handle more expressive properties. So modulo non-convex slices, could be modulo lattices. And then here is the work it's really an ongoing work. We have some results at this day. So here we prove at the end of a sort algorithm that the array is sorted, but it could be a field of 0. We don't know. So we have to prove that the output array is a permutation of the input array. So we have an abstract domain of reasoning about multisets of values. So here is the end of my talk, and I can give you a demo about the analyzer. Oh, it works.
So
Oh, we are lucky.
It's fully automatic only in the sense that
Yes, as you,
that there is a proof which is based on partitions. If there is no proof which is based on partitions, then you cannot claim that your method is automatic.
First, I have to say that, as usual in abstract interpretation, you have to choose the abstract domain. So here, ln and lc. And then it is fully automatic. I'm not...
In the sense, and the partition is encoded into the ln or NLC, right?
Yes, yes.
Okay.
And so you have this point, and then, of course, it could be that the partition we decide is not refined as needed to find the property, of course. So we have to think about refinement during the analysis.
And the one LNLC we should experiment with is the partition stuff.
Yes, we choose ln and lc for all the examples, the same ln and lc lattices, which was DBM, difference bound matrices, or potential constraints. So it seems that you do not have to always change your lattices. You can. So our analyzer can handle different lattices. So you can. Okay, I first want to analyze an array copy program. So our programs are written in a language named FAST, which is a label transition system language. So here, for example, you can analyze an array copy with a lattice like DBM. So you will throw away things about arrays. And okay, the output is at the moment a little bit difficult to read. So I will show you the program. Could be a nice idea. So you declare some states, some arrays, some variables, and then you declare some transitions. Transition from which state to which state.
It's not very readable.
Yeah. Yes. We at the moment we work on a C. On a C language. Okay. We will. So, can you look here? Yeah, you see it. So at the beginning you put I equal 1 and x equal 5. I will have another variable, a content variable x. And then how I do that? Just a minute.
Can you move the page to the center of the screen?
Can I?
Move the page to the center of the screen?
Yeah. Okay. It was a good idea. Okay, so you will enter into the loop if I is 0 equal to n, and then you copy b into a, and you make the incrementation, and at the final you exit the loop if I is strictly greater than n. Okay.
Can you explain the meaning of each of these transitions? So what is this from to guard?
Oh, from is okay. You have some states, init, loop. Oh, could be.
What
No. It's I is only the index variable. It's a scalar variable. Could be that I have a nice view of this. Okay, could be better. So at the beginning, I assign 1 to I, and then I enter the loop if I is lower or equal to n. I make the assignment of B in A, and in the incrementation, and the n is when I is strictly lower than n.
So do you always assume
Okay, here are states are here of what is the transition is. It's not the state. It's
So from a textual description, it looks like you are always assuming that loops have the form I equals some initial value, I less than some final value. Is this the case?
yeah, it's for like loops. Yeah.
So can't you write more arbitrary loops here? Or?
Okay, but yeah, it's of course you cannot change, for example, the values of your index during in the loop. Things like that. Or you can, but you will lose a lot of information. So it is just I said, you can, yeah, always incrementation or decrementation. Basically, if you remember when we do the incrementation and we have the join of mu1 and mu2 that holds between the cell I, if you had done an incrementation by 2, you will have also to consider the properties mu3. So we have to join all the properties you know in your array.
So you designed this language just for this one?
No. It's a language, a French language in a rare laboratory.
And it's used for reasoning about like numerical analysis.
No, the point is that I had to do a static analyzer, and I had to start that with what is in my lab at that moment. So the entry language was this one.
No, so I'm just asking, I'm just curious, like why do they use this language instead of writing C programs?
Oh, basically they do, how do you say it? Pressburger arithmetic analysis of the program. It is, yeah. So now we have seen the program. So I will go directly to the analysis by arrays. And then, okay, don't be afraid. So you have here and then more at top the property that holds at each control point. Okay, so I remember you have init, loop, f, and final control point. And then you have the property about indices till a one point, and then you have properties about arrays beginning with forall L, such that L is something. You will have an imply, for example. Okay, here, for example, for all L. I'm sorry about that. We changed our our output to be better, and it's worse at this time. So what we want is the equality between A and B, and it's here. So for all L, so that L is, I think, lower equal than I. Okay. And I is greater than 2, and L is greater than 1. I have B0 is greater than A0, and A0 is greater than B0. So the end give me the equality of A and B. And just see that you have x is equal to 5 in each of the 3 symbolic slices. Okay? If now I put that I have n is strictly is greater than 1, and make an incrementation of x also, at the end of the program I will have at least one incrementation of x. And here we see that indeed, okay, we have x is greater than 6 on all symbolic slices, which was what I spoke about before, scalar consistency in your slice properties. Because I is greater than 2, because I do at least one step, of course x is greater than 6. And then we can do some other example, maximum search, for example. So here, maximum search, you will find that A0 is low equal to m. M is the maximum scale, the scalar variable representing the maximum value. You can also see Sentinel. So for the Sentinel, the things to see, oh, I will make a bigger screen. So what you want to have is that the property about indices is that I is lower equal than n, that you stayed into the bounds. So you have it in final, and loop, you have also I is lower equal to n. So you ensure that you are always within the bounds. And finally, insertion sort algorithm. What are you doing? So as expected, it's between 5 and 6 seconds. And at the final control point, you have here that A0 is greater than A1 for all L, such that L is low equal to I minus 1. So it is what you wanted. So here is the end of my demo. Thank you for your attention. If you have questions, I will be pleased to answer them.
Any questions? Thank the speaker.